The basic rules derived from a physical sense of control volume method. The formulas from the previous lesson provide sufficient background to allow the formulation of the basic rules that our discretization equations should obey, to ensure physical realism and overall balance. These simple rules have far-reaching implication, and they will guide the development of methods throughout this course. Rule 1. Consistency at control volume phases. When a phase is common to two adjacent control volumes, the flux across it must be represented by the same expression in the discretization equations for the two control volumes. Discussion. Obviously, the heat flux that leaves one control volume through a particular phase must be identical to the flux that enters the next control volume through the same phase. Otherwise, the overall balance will not be satisfied. Although this requirement is easy to understand, subtle violation must be watched for. For the control volume shown in figure 2.2, we could be evaluated the interface heat fluxes lambda dt by dx from the quadratic profile passing through T sub V, T sub P, and T sub E. The use of the same kind of formulation for the next control volume implies that the gradient dt by dx at the common interface is calculated from the different profiles, depending on which control volume is being considered. The resulting consistency in dt by dx, and hence in the heat flux, is sketched in figure 2.4. Another practice that could lead to flux inconsistency is to assume that the fluxes at the faces of a given control volume are all governed by the center point conductivity lambda sub p. Then the heat flux at the interface E, shown in figure 2.2, will be expressed as lambda p multiplied by T p minus T capital E over delta x sub E, when the control volume surrounding the point P is considered, and as lambda sub E capital E multiplied by Tp minus Te over delta x sub E, when the equation with capital E at the center point is constructed. To avoid such inconsistencies, it is useful to remember that an interface flux must be considered in its own right and not as belonging to a certain column volume. Rule 2. Positive coefficients. Most situations of interest here will be such that the value of a dependent variable at a grid point is influenced by the values at neighboring grid points only through the processes of convection and diffusion. Then it follows that an increase in the value at one grid point should, with the other conditions remaining unchanged, lead to an increase and not a decrease in the value at the neighboring grid point. In equation 2.17, if an increase in T sub capital E must lead to an increase in T sub capital P, it follows that coefficients A, E and A, P must have the same sign. In other words, for the general equation 2.19, the neighbor coefficients A sub n B and the center point coefficient A sub capital P all must be of the same sign. We can of course choose to make them all positive or all negative. Let us decide to write our discretization equations such that the coefficients that are positive. Then rule 2 can be stated as follows. All coefficients AP and neighbor coefficients A sub n B must always be positive. Comments. The coefficient definitions given in equation 2.18 show that our illustrative discretization equation 2.17, does obey the positive coefficient rule. However, there are numerous formulations that frequently violate this rule. Usually, the consequence is a physical unrealistic solution. The presence of a negative neighbor coefficients can lead to the situation in which an increase in a boundary temperature causes the temperature at the adjacent grid point to decrease. We shall accept only those formulations that guarantee positive coefficients under all circumstances. Rule 3. Negative slope linearization of the source term. If we consider the coefficient definitions in equation 2.18, it appears that even if the neighbor coefficients are positive, the center point coefficient AP can become negative via the S sub capital P term. Of course, the danger can be completely avoided by requiring that S P will not be positive. Thus, we formulate Rule 3 as follows. When the source term is linearized as S middle is equaling S sub capital C blue plus S P T P, the coefficient S sub capital P must always be less than or equal to 0. Some remarks. This rule is not as arbitrary as it sounds. Most physical processes do have a negative slope relationship between the source term and the dependent variable. Indeed, if SP were positive, the physical situation could become unstable. A positive S sub capital P implies that ST sub P increases, the source term increases. If the effective heat removal mechanism is not available, this may in turn lead to an increase in Tp, and so on. Computationally, it is vital to keep S sub P negative so that instabilities and physically unrealistic solutions do not arise. The third term, linearization, is further discussed in the next courses. It is sufficient to note here that for computational success, the principle of negative S sub capital P is essential.